Hello, in this video we will put to practice a concept that we learned in the last video, which is how to solve systems using the inverse matrix. So if we were to have these systems of equations, which we actually had in the video where we practiced and learned Cramer's rule, we we can transform it into the form that we want it to have, so that then we can get the inverse of the matrix and find the value for x and y. So I like to use this example to show you that actually doesn't matter what technique you use, you always get the same result. So as you might recall, we will put the coefficients of x and y in this matrix right here, which we will call A. Then x and y right here. So by having x on top, it means that these are the coefficients of x, and by having y at the bottom, we are saying that these are the coefficients of y. Actually, we could have the matrix right here like this: 2, 3, 5, 2, and just flip y and x, and we actually get exactly the same thing, and that is equal to 16 and 13. And we would have 2y plus 5x is equal to 16, and 3y plus 2x is equal to 13, which is exactly the same thing we have here. So, but just to keep it easier and more consistent, I will do it this way, but just so you know that you can move things around, but as long as you understand why why do we have things in this given order, and how you can manipulate the matrices and get the same result, I think that's useful. That's good to know. But so right now we have this right here, and we will work with this, and this is equal to 16 and 13. So now, as you might recall, we will multiply both sides by the inverse of A to solve for x and y. So we will now find the inverse of this matrix right here. So this is our matrix. As you might recall, the inverse, we have 1 over the determinant times, and we flip it, so 3, 5, and we get the negative of this diagonal right here, so negative 2 and negative 2. And the determinant is 15 minus 4, and that is equal to 11. So we will have an 11 right here. So now this is equal to 3 over 11, negative 2 over 11, negative 2 over 11, and 5 over 11. And this is equal to the inverse. So now we have that x, y is equal to, and remember that our inverse matrix goes at the front, and it's 3 over 11, negative 2 over 11, negative 2 over 11, and 5 over 11, and that times 16 and 13. And so now we must multiply these two matrices. So first row times column. So I'm just going to factor out a 1 over 11. I don't think it was such a good idea to multiply by the scalar first, because we get kind of ugly numbers. So I'm just going to take out for a little bit the 1 over 11. And so we have 3 times 16, that's 48, minus 2 times 13, that's 26. So minus 26. And so this is equal to 22. So we will replace this with a 22. And now our second row times our column. So negative 2 times 16 is negative 32. And then 5 times 13 is 65. So 65 minus 32, that's 33. So we will replace this with a 33. And now we can multiply by the scalar. I just want to remind you that you could have done it just by multiplying 16 times 3 over 11, but I just thought it would be easier just to factor out the 1 over 11 to leave friendly numbers in the matrix and then multiply the scalar. This again doesn't change the result. If you are not sure about it, feel free to do it one way and the other to make sure that we're consistent and it's the same thing. So now if we multiply this by the scalar, we get 1 over 11 times 22 is just 2, and 1 over 11 times 33 is just 3. And we have that this is equal to x, y. And so x is equal to 2 and y is equal to 3. Very well, now just to make sure, I'm going to show you a screenshot of what we got when we used Cramer's rule. And so here, this is a screenshot of that other video, and you can see that we found y to be equal to 3, which is exactly what we got here, and x to be equal to 2 right here, which is exactly what we got here. So we got the same answer using different methods, and that's the beauty of matrices, that you can actually manipulate them in many ways and still get the same answer.